after a couple of attempts to connect the audio to the interfaces here. It's a little bit difficult. Welcome, everybody, to I think our last lecture on physical and database modeling. Even if there is one indicated for next week, we will see that probably we can end up today with and finalize our topics. Just to start to begin with, we have here our topic, chapter 6 on physical interpretable modeling. And the idea is to include some sort of additional information like, well, control systems knowledge, controllability, observability properties, as well as some properties of the physics of the nature of the behavior of the system, like using continuous time dynamics instead of having discrete time systems, which are a little bit more difficult to interpret compared to the continuous time dynamics. We discovered that in the very first two chapters, that in continuous time the systems are working. So we end up with differential equations, continuous time differential equations, and not discrete time systems. From an implementation point of view, they are both interesting, but well, if you want to understand the physics behind it, it's of interest to have this discrete time thing. So basically, we want to finalize that. Last time we learned a little bit about the subspace identification method. Well, the story starts. I just wanted to show that it's somehow a little bit different to what we learned before. It's two-step procedure compared to the squares estimation things before. And then we jumped into the algebraic method, and that's what I want to do right now also. Let's go to that. So a fast forward. We learned something about how to do that, and I want to summarize the basic steps and perhaps reduce this one to enhance readability. So we start with some sort of the Laplace transform. The Laplace transform is in that case helpful because we can do all the manipulations easily, and therefore it's called algebraic method. And the idea is to transform the ODE. Then we try to get rid of some sort of disturbances. In particular, constant disturbances can be rejected completely. It's important because we are able to do the derivative with respect to the variable s in the image domain, which is, I think, the first time you use this kind of plus transform formalism. Later on, you try to reduce the number of derivatives in the equations by dividing with s. And last but not least, we transform it back into the time domain, end up with with one single equation with integrals, and this integral setting is therefore helpful because we then do not have to do derivatives of measured signals, which pose problems in practice if these signals are distorted by noise or so. At the very end, we have this single equation, and then we want to get the information for the parameters. If we have more than one parameter, then obviously we need more equations, and these equations can be generated in basically two ways. One way is looking at different time spans. So T0 to T1, T1 to T2, for example. And if you have 3, 4, 5 parameters, you can look at different time spans. And second, we can also integrate the equation a couple of times, which is possible or a reduced number of parameters to be identified, but might become a little bit more too complex. If we have 10 or 20 parameters, then you need 20 integrations and 20 integrals. Well, even from a numeric point of view, it's not feasible at that point. So, but at the very end, you end up with a set of equations, a set of parameters. You can put this again in a least squares formalism and ask and solve for the parameters. And the question I asked last time is, if we end up with something looking like that, but instead of having just two equations for two parameters A and B here in this example last lecture, we have perhaps 10 equations. And assuming that we have some sort of noise at the output, so y, it's not y, but y plus epsilon, some white noise, the question appeared, do we get a consistent estimate? Was somehow left to your homework to think a little bit about that. And now I checked the homework. And so question is, what do you think? Do we get a consistent estimation of the parameters if we have more equations, noise? Hopefully with more equations, we get better estimates, of course. But do we get a consistent estimate? Remember, consistency is composed basically of two facts, bias-freeness and a variance which is limited, at least, not infinite. So these two questions have to be answered. What do you believe? Perhaps you can raise your hand. So we have two options, so 50% chance for each of us. What do you believe? Is it consistent or not? First, consistent. One. Non-consistent. Third option is not present. Yeah. Might be that. Mean zero? Yes. So if the time interval here, at that point, we have no time interval spent so far. So, and in my last lecture, I added something, is T0 to T1, so remained open. So we can believe or assume that if the time span is quite long, then the white noise cancels out somehow on the one hand. But remember, if you think of your lecture on least squares, what was the main fact if we looked at the basic procedure for linear least squares estimation, because it's a linear setting, so we have the same situation as before, linear least squares estimation for dynamic systems. Do you remember the problem there? Somehow it was unfortunately not consistent for the dynamic systems due to the fact that some entries in the matrix M, was also called M at that point, are correlated with other parts of the matrices due to the fact that we use yk minus 1, yk minus 2, so the history values of y, and the distorted history values of y. So we cannot believe that there is no correlation. So is this somehow different to what we have here? Well, basically, so roughly speaking, yes, we have the same situation because here you have y here and there. So we have similar integrals. So we cannot expect that there is no correlation between the entries of M here. So in this particular example might work, but in general, so you have entries of y, integral y in the next row and columns, again, some sort of integrals and the noise. So basically, we cannot expect that the entries are uncorrelated. And in the most general case, so the general answer is, unfortunately, the consistency cannot be proved in a general setting. So due to the case that we have correlation between the entries there. But something which you already mentioned is also important and interesting, because somehow if we have a long time span, we can think that these integrals somehow smooth the things out. So yes, it's correlated, but the value of the noise might be limited or small due to the fact what you mentioned. So engineering experience, and we're an engineering class, engineering experience shows it works pretty well in practice, due to exactly these facts, due to the integrals, because the integrals somehow, reduce the noise. Even if it's not a pure filter, what you learned in signals and systems and all these things. No, but we smooth somehow these white noise out, and therefore it works well in practice. On the other hand, theoretically proven, it can't be theoretically proved. That's the problem, and that's interesting at that point. So therefore it works well. On the other hand, we have a lot to do. So if we do all these things here again, we have some pros, no discretization, clever manipulations, and the interesting fact, you can eliminate constant and sinusoidal disturbances. We will see this in a second procedure again. And this is really, really interesting because, for example, we use this procedure for battery system identification, so identification of battery parameters. It's a little bit more complex there because the battery is even more complex than the simple LTI system. I come to this back later, but there we usually had some sort of distortion due to the frequency of the 50 hertz frequency. And if you look at the signal to noise ratio, we gained compared to traditional methods which you learn in material science, like impedance spectroscopy. We realized that the signal to noise ratio were completely different in that sense that this method worked better, substantially better. We speak about 20 to 40 dBs, and this is really substantial at that point. We were able to reject a lot of these disturbances. So from a practical view, it was a little bit surprising at that point. It helped. So on the one hand, these pros, so you can completely reject that, and you get good solutions. I can add, and that's research work dating back almost 10 years of our research group. We were able to put this in a more complex setting. Batteries live, for example, partial differential equation setting, where batteries, if you look at the partial differential equations only at the connectors, because every battery has just these two connectors or each cell, then you get a specific linear system which describes the behavior very well, with the interesting fact having the so-called fractional systems, and fractional systems are systems where, let's take this one, M and N are fractions of really fractions, so 3/4, a half, and something. That's sounds strange. So it's something like a half of a derivative. It's fascinating at that point, and it somehow describes the behavior of this partial the diffusion processes inside of that, and can be observed if you look at the impedance spectroscopy of such systems. So it can be, well, extended to that, and well, works well. But on the other hand, yeah, we have the calculations here might be, well, really tedious, complex, a lot of work. And some of the equations have to be written down. Even writing this down is perhaps a little bit too difficult. Well, the numerical procedures behind are well elaborated and well known. So quadrature for integrating and multiplication and summation, that works well. But the computational complexity, if you have more than, well, say 5 to 10 parameters, becomes infeasible. Well, we then realized there might be a different procedure. This is also something which is interesting. You realize something, and then you realize somebody else had the same idea already, not just recently, but 30 or 40 years away. So, well, if you I go back to the I go back to that. So if you look at the very formulas, you see, well, on the one hand, there are integrations, right? So integrations of the signals, and a combination of U and Y. But there's also something mysterious here. There's an integration over, take it this one here, over T times U. So there's a function which is multiplied with the original signal and then integrated, right? Well, why not generalizing this? So why not multiplying everything with a general function, gamma, and then integrate and look what happens? This was the initial idea. So like naively, well, playing a little bit with the formula and saying, well, the most general case of that would be, instead of taking this one, you're taking gamma times U and then integrate, or gamma times Y and that. So, and this is the starting point of a second procedure. Unfortunately, when we discovered that, we realized, well, it's already existing. So, and it's called modulation function method. And it was invented already in the 1970s something, really old, and then disappear completely, like the algebraic method. Disappear completely because everybody realized, yes, nice continuous time systems, but we have discrete time data, just sampling time, so we are not able to work with continuous time signals, just simple data systems. So everybody moved in the 80s to simple data systems, and then, well, all these continuous time methods disappeared. And, well, a colleague told me, well, hey, Søren, there is something which is similar to what you did. Well, this is nice and not nice. Not nice from a research perspective, because somebody says, well, it's already done. Nice that if you see who did it, it's nice. Well, I'm not so stupid, so it's also interesting. So it was not me; it was a research assistant, and I always say, this is the first. If the first frustration ended, you should laugh, because you see you're not the stupid man or guy or woman. You learn something. Sometimes this happens, right? So sometimes this happens. If you realize that you discovered something Kalman discovered, you can be happy, right? Okay, so I just want to explain the method. A bit later on, we realized we can go further in other directions which do not exist. But for the basic procedure here, so we did that very same thing for batteries again, and other things which after a while showed that there's a huge area and control theory not existing, and we worked on that. So was the inspiring starting point, perhaps. So again, we start with somehow an ODE, which is given a u of t is equal to y of t plus b u of dot of t. And now what we're doing, we multiply this equation with gamma. I talk about the gamma a little bit later, and then we integrate in the interval 0 te. Now what happens? We get gamma au, gamma y, and gamma y dot, and b, and all the parameters. And now we use a simple rule. In particular, we use the integration by parts rule, and this helps to avoid something which we want to avoid. We want to avoid the differentiation of y, right? Because we do not like differentiation of signals due to noise considerations. So if we do that, reminder, integration by parts, you remember that. So f prime times g is f times g, f g prime. And you say, well, yeah, looks nice, but now I have g prime. Well, again, a derivative, but let's do it. So we did it here. Gamma u, well, nothing. Gamma y, nothing, is similar to what we had in the algebraic method. But now here it comes. Gamma y dot gives gamma dot times y. Well, and the rest. Okay, so now suppose you know gamma, and the computer, it's perfectly known. Then of course you can calculate the derivative. There is no noise. So what is the funny thing? You shift by integration by parts the problem from derivatives of y to the derivatives of gamma, but derivatives of gamma are not so problematic, right? And that's why this procedure works quite well. Now this remains. Okay, now let's talk about gamma a little bit. And the very first idea is to say, okay, gamma should be constructed like as a function which is 0 at 0 and 0 at te, because then this disappears. And we can look at, so that's the first idea, and we end up with this equation. Okay, the only thing I did, I put b and a. No, here I forgot it. Okay, usually I should put a here in front of the integral, so I have an equation where I separated more or less a and b from the rest. And if you do so, you end up with, again, a simple equation like gamma y is equal to a vector m transpose times ab, which are the unknown parameters theta. So we get z is equal to m times theta, similar to what we know from the algebraic method, right? So at the very end, we have one equation. Now we can use the very same trick as before. We can use different integration intervals, T0 to TE, TE to T1, etc. So to generate more equations, well, at least two to get A and B. And now this looks similar to the algebraic method, but it isn't. It's particular because now we get a degree of freedom, and the degree of freedom is gamma, the function gamma. This is nice. So if you have a degree of freedom, it's nice because you have the degree of freedom, but it's not so nice because you have to choose it. So the question appears how to choose gamma, and which fulfills at least the two conditions. Gamma of t0, t equal to 0 should be 0, and gamma of t equal to te is equal to 0 as well. So that's the question. And but if we look at the final result, okay, derivatives of y have been eliminated. We have a simple situation. We can expect the very same as before. And again, the question, can we in general prove that this procedure produces some sort of consistent estimates? No. Same problem as before. Because we get some sort of correlations between the signals. And that poses again problems. But again, engineering experience, same result as before. The noise is a little bit reduced due to the integration, so it's flattened. We get good results. And again, battery story, it worked quite well. But there is also a second way of generating more equations. You can choose different gammas. You multiply the entire equation here on top here with gamma 1, and then again with gamma 2, gamma 3, gamma 4, gamma 6, etc. So this brings us to this setting, and then we get the estimates of the parameters so far. Now, the question is, what kind of gammas exist? What are present? And if you look in the literature after realizing that, well, unfortunately, this procedure existed already, when we discovered that, existed already, there was a vast literature on how to produce these gamma functions, the so-called modulation functions. Well, modulation, by the way, it's a similar story the communication engineers are doing. So that's why. Well, of course, you can use so-called spline functions, which are at that point here 8, I think we choose, and 0, exactly 0. So it's something in between. These spline functions, well, can be different. So you can generate, well, a bunch of splines which fulfill this property. There are three trigonometric functions which are also working. These are particularly relevant because if you multiply a sine combination with sine signals, you can cancel out noise completely, which is sinusoidal. So in particular, if you have 5 to 50 hertz problems in measurements, you can use this method easily, and you can get a signal to noise ratio of infinity. So really, really big. And polynomial functions. So these are functions which have been, well, researched for, looked in practical applications, etc., and work well. And the question is there a way of generating these functions automatically? And the answer is yes. Is there an optimal function in some sort of reducing noise? Yes. And this was the research we did later on. And so we can say that the very these modulation functions can be generated automatically, etc., etc. This is not a story for us. But this should show that even if you start and you're frustrated at the very end, you find something which is also interesting because the modulation function story did not exist at that point. So some sort of pros and cons. Again, the problem is completely independent of the initial values of the measurements. That's important. Second, no derivatives are needed because we reduce noise by integration. There are no discretization situations, so we get continuous time systems directly. We never. So by the way, it pops up first up. It can be extended to time variant models. Last, we need linearly independent modulation functions have to be calculated, but there exist such classes and they can be generated automatically in some sense. So at the very end, it works quite well. So from our perspective in practice, what nobody did even if it's probably only a small thing, whether this kind of procedure also applies to differential algebraic systems. Because if you start there, you can directly identify the differential algebraic system. I never tried it. Pops up into my mind. If you think of chapter 2 and 3, remember at the very end, we end up with a differential algebraic system, right? So nobody did it. So if you want to have fun, you can try. It's, as far as I know, an open question. So it has not been done so far. Well, if you, there is some thesis of my former PhD students working on that for battery systems, and then the theory became really complex, I should say. Please, well, if you want to have a lot of mathematics, you can look at these theses, because they try to extend this to partial differential equations, in particular these fractional system things, which apply to batteries very well. But it worked well there, and some sort of theory for these fractional systems appeared during this time. So this is some part which is interesting. So at the very end, we end up with a method which allows to identify the continuous time system directly. If we look at that from a historic point of view, we see, okay, in the past, these discrete time system approaches are the most relevant ones, due to the fact that we have discrete time systems. We have to implement everything in discrete time. Why not directly using discrete time signals and work with that? That's one position. Later, one realized that discrete time systems, yes, they are wonderful, but very often physical insights are helpful. And today we have sampling devices which are substantially fast. We can continue with an almost continuous signal. So it makes sense to work with these continuous signals. And why not identifying the continuous time system again? So that's the situation. By the way, why this method, the modulation function method, appeared during the time where we had no computers, almost nothing. So, and at that time, a lot of continuous time circuits were realized to produce multiplication, derivatives, addition, etc. So realizing with traditional circuits, we had such a computer in my institute, was, well, from here to there. And there, implementing such a modulation function approach worked on a continuous time computer, but it completely disappeared as at that. So today it's even more relevant. But if we look at our considerations in chapter 2, 3, and 4, you might remember that, well, yes, okay, the network perspective yield differential equations and all that. But later on, we realized that the governing principle is a optimality condition. So the principle of least action, if you remember. So the idea was to say, okay, if we have a physical object, the principle of least action says minimize the action, then you get the differential equations. So theoretically speaking, the question appears, why should we identify the differential equations? It's even better to identify the objective function, right? From data. Suppose you have the data, and we know physics behaves according to an optimality principle. Why not directly identifying the objective function? So the Lagrange function or the integral of the Lagrange function. That's the question. And this was the starting point of the so-called, I'm going forward, inverse optimal control. So you learned something about optimal control in the lecture on ODS. And here the question pops up. Well, we want to do the inverse way. And I want to explain what I mean with that. So why that? Because we get physical insights, because physics is generated by energies, and so it would be interesting to get the energy describing principles. And that's ongoing research, and therefore it's called Outlook. It's not completely done so far, and I want to show you some examples. So chapter 3 and 4 had the idea to show that there is a forward question. Given the definition of action, what is the ODE? What are the trajectories generated by that? So this is the forward question. So remember ODS, you start with a performance index, dynamic setting, you do your calculations, you end up with the either with the Euler-Lagrange differential equation, the Hamilton differential equation, or even the Hamilton-Jacobi-Bellman equation, if you like. So it's more compact. And then you get ODEs. You solve the ODEs, you get the trajectories. You can plot the trajectories or see, okay, the ball is behaving like this. That's the forward question. And now we are looking for the inverse problem. Given the trajectories, so you have measurements of the continuous time measurements of the trajectories of a physical object, and you're interested in the governing principle, so the action, basically, or the function which is under the integral. That's the question. I want to show you some examples where this happens. And some are depicted here. One question is on the left-hand side, just to show you importance of that. Suppose you want to describe the behavior of a car if it does a lane change. This is a problem which appears quite often. You want to predict whether a driver does a lane change, for example, or how the driver will drive in the next 20 minutes or so, or 1 minute, or 10 seconds, or 3 seconds, or 1 second. Well, the first second can be easily described because if you know the steering angle, then know the physics of the car. So, well, it will turn according to a circle adjusted by the steering angle. So that's clear. And that's also helpful because the car can't behave differently than the car does before. But if you want to predict something like 8 seconds, well, it's more difficult because the driver can do this one and that one, etc. So the question appears: can we identify the behavior of the car, including the driver? Is this possible? Second example: if you have the last I leave out, if you have something like that, this is a exoskeleton, a little bit large for therapeutic rehabilitation. There you do walking, right? So suppose the patient is not completely disabled, he still can walk. Then it's obviously necessary to know what the patient is doing, right? So it's necessary to know the behavior, the movement of the patient, right? And the problem, otherwise the robot is doing something, the human doesn't want to do. So the behavior of the human is of importance of such cooperative systems. So necessary information. And therefore, we can say the problem of identifying what the physics is, what is describing the physics is of interest. Why? Because if you know the objective function of the physical system, then of course you have a good predictor for the future, or you can simulate, or you can use it as a design criterion for cooperative system or whatever. And the interesting fact is, if you know the basic principle, it generalizes. That's the idea, right? Well, there are basically two perspectives. I come back to that later on again. There are basically two perspectives today in the world to do that. Everything is okay? Basically two perspectives. One is you do so-called behavioral cloning. That's what the robotics guys are doing right now. Behavioral cloning means, well, you observe trajectories and you're trying to train a neural network which does the same. Okay? Well, I can ask you to come forward and do a work, and we compare your way of going moving from left to right and my way. You will see it's completely different, even if we move forward. So, is it completely different? Well, that's the question, but there are movements where the human is behaving differently. So behavioral cloning is wonderful to describe the particular movement, one particular situation, and even the human itself is behaving differently. So if I'm angry, I'm moving differently than if I'm not so angry. You can observe this if you look at car drivers, if they are angry or not angry. So that's of interest. But the problem with behavior cloning on the one hand is it does not easily generalize to problems. So the question in the robotics community is, what do we have to do in behavior cloning such that these things generalize? Not my story, but the story there. To describe the human movement, for example, in cooperation with another physical entity. You can go differently. You can say, okay, we know human movements are described by an optimality principle. We know that already, more or less good, that the human movement is described by the optimality principle. Let's try to identify the optimality principle directly, then it should generalize. So we have it in our hands. That's the way we are doing that. But then the problem appears, is it possible to identify the objective function out of data? First of all, yeah, this is a little bit how the problem was set. It was first described that way by Norrie and Fraser, and the very first question was posed by Kalman. Interesting. So it's rather old, but not answered so far, or completely answered. So back to there. But there are good news or bad news, and bad news. Good news, it's possible. Bad news, the problem is ill-posed. I want to say some words about ill-posedness. It's easy to understand because if you remember your ODS knowledge, you remember that the optimization of the objective function J is equal to the integral of x transpose qx, for example, times a half gives the same optimal trajectories like times 5. Scaling does not change the solution. And if the situation is even more complex, you have some sort of the same different objective functions yield the same trajectories. It's non-unique. If you pose the inverse problem, you cannot expect to get the particular objective function. You can only hope for getting the entire set of objective functions, which are describing the situation. So this is one problem, right? Okay. But on the other hand, it's possible, since more or less 5 years, to describe in some settings the so-called equivalence classes of the objective functions which do the job. So now let's determine it a little bit more precise. The inverse optimal control problem is set as follows. Given observed trajectories, suppose they are optimal, what is the objective function J which produces these trajectory? So remember optimal control, given the objective function, what are the trajectories? Now, given the trajectories, what are the objective functions? That's functions, usually. So we are interested in this inverse problem. And there are basically 3 approaches. One is the direct approach. It's called bilevel method. That's the most naive way to do it. Was the first way to do it. Then there exists a set of inverse optimal control methods. And last but not least, there is also a training method, which is called inverse reinforcement learning. They are similar, not equal. So let's talk a little bit about this. Due to the fact that we have not learned anything about reinforcement learning, it's difficult to speak about inverse reinforcement learning. So therefore, I leave that out. If you're interested in that, come to us and do research in this topic. But the first are also interesting enough at that point. So start with the bilevel method. The bilevel method works as follows. We suppose you are able to compare the optimal trajectory produced by an optimization with the measured trajectories. Then we can do the following. You can use an objective function which is parameterized. Okay, you take an objective function, took 3 parameters in it, and put it in the forward solution and optimize over the parameters. Right? So you have 2 optimization cycles. One for solving the dynamic optimization problem and one for adjusting the parameters. If you remember your understood, right? So objective function J depends on theta, and the parameter theta is unknown. It's like setting a objective function up where the Q and R and S are unknown. And then you tune these parameters such that these 2 trajectories, the one calculated and the one measured, fit. And tuning these parameters is again an optimization problem. So you have 2 optimization problems. One classical static optimization problem as an outer loop and an inner loop, which calculates the dynamic optimization problem. Well, this is called bilevel method because you have an outer and inner loop, 2 levels. That's why bilevel. And it was the first approaches started to work in that way. To identify, by the way, one person who did it the first time for robots is teaching here at KIT. It's Katja Mombau, for example. So Katja did exactly that and tried to have this outer loop and this inner loop. What might be the problem? What do you think? If you think of this tactic. Of course, think of perhaps computational complexity a little bit. What's about that? Do you think about that? Yeah. High, low, easy, perhaps difficult, right? That's the problem. So if I ask that why it's difficult, it costs really time. Why? Suppose you have the outer loop is optimizing something which is an optimal control problem. The optimal control problem is neither convex nor, perhaps depending on the method used, nor continuous. So no second order derivative, no first order derivative. And the inner loop itself takes time. So remember, solving an optimization problem becomes problematic. Now you put it in a loop. You solve not just one, but millions of these optimization problems. Therefore, the computation, for example, for a movement of the arm from point A to point B took, days, even on the fastest computers last, 3-5 years ago. So really long-lasting calculations. That's one way, but it works. So the lower level somehow determine the optimal trajectories, and then we have at the upper level which calculates the parameters and adjusts the parameters. That's the basic idea. And at that time, everybody thought of, the problem is the lower level calculating the optimal trajectories, because the faster this level is, the faster I can calculate the inverse problem. So everybody was seeking for efficient numeric procedures, right? But unfortunately, this does not went well. On the other hand, there's a second way. There's a so-called inverse optimal control based on first order derivatives and optimality principles. And that was the way which appeared a little bit later. And the idea is the following. If you remember your ODS knowledge, you know that there's a necessary condition that a trajectory is optimal. We use that here also in our lecture in the chapter Action Minimization. The first order necessary condition is that the first order variation vanishes, right? So the variation of the objective function should be 0. That's a necessary condition. So why not using this necessary condition? Perhaps it helps. And this was the idea invented in 2014 or something. So not long ago. And then we can do the following. We can compare the actual trajectories with regard to the first order necessary conditions. And this is possible. And then assume, if they are optimal, this residuum must be 0, as we know. The first order variation must be 0. And if it's not, we can tune the parameters according to that principle. And the interesting fact is, I will show you this for a simple case. The interesting fact is you can completely avoid one loop. And this speeds the problem up by factor, depending a little bit on the problem, 100 to up to 1 million. Even here in the slides, it's a little bit conservative, but we had also factors 1 million. You get the calculation within seconds. And this is interesting. Well, let's do it for a simple problem. Suppose the we focus on the linear quadratic problem. Given is the following optimal control problem, and we are interested in Q and R. So the forward problem is given by means of solve this, and now given A and B, and now we have the inverse problem given X and U, what is Q and R? And, well, you know everything for that. Remember, the optimal control problem is solved by means of the Riccati equation. So any solution of the quadratic optimal control problem has to fulfill the Riccati equation. And if you remember the Riccati equation, well, there's a zero. And now the question appears, if I tune the parameters some way, is it possible to achieve zero there? So let's have a look at that. So first of all, we know it's a closed loop system. F is equal to I minus BK. And what we also can do is we can reformulate the Riccati equation differently in such a way that the parameters Q and R are on the right-hand side. This can be done by means of the so-called Kronecker product and the vectorization of a matrix. This is looks horrible, but it's trivial because you just staple the matrix elements one on another. That's all. If you do so, at the very end, you get a situation where you have this matrix here multiplied with a set parameters. W times theta is equal to 0. It's just reformulating this equation here, right? Well, if we can do that, we have the parameters on the right-hand side, and we end up with the following situation. We can formulate the problem as a quadratic program and now calculate W as a minimizer of this problem here, and giving the solution such that this matrix Riccati equation is fulfilled, right? That's the basic idea. So you can use the information that you know every solution which is quadratically or has a quadratic performance index has to fulfill the matrix Riccati equation. And if it's not fulfilled, I have the wrong parameters, right? And therefore, we can adjust the parameters according to that. That's the basic idea. And this applies to linear systems, nonlinear systems, etc. And works quite well. So at the very end, for the LQ case, it's simple. If we have this one in bi-level approach, it takes really hours to calculate even simple systems. There you get a speed up of millions. If you look at nonlinear systems, it's not that much because you have still an optimization problem in between. But this is then you have a speed up 10 to 100, sometimes 1000. So direct method, the indirect method, if you like. Yes, that's the point. Why we are working with that? Because we wanted to describe what happens if a human and a machine are working together. This way, for example, you move the machine and you are moving one table. So a robot and myself trying to shift this table from left to right. Then obviously it's necessary to describe this interrelation between the human and the machine. And our idea was, well, if the human is an optimal controller, then obviously at the very end, it's necessary to describe the human as an optimal control problem, starting that way. Then why not using a copy of that for the machine? So also an optimal control problem. Then you have two optimal control problems. If two optimal control problems are acting together, you end up with unfortunately, a dynamic game. So they are playing together. And when we first discovered that, we thought, why not using this behavior and looking whether this works well for cooperative systems. So one system is the machine and one system is the human. And at the very end, in our first experiments, it worked well. So I thought, nice shot. Then we tried it in another experiment, different situation, worked also well. So we had after another, this principle worked well. And this is the interesting fact about that. But then I discussed with a colleague of mine, and she said, yes, worked well, yes, but where do you get the performance index of the human? And then this research started. Say, yes, she's right. Well, there's a point. We do not know the performance index of the human during the cooperation. And so the question appeared, is it possible to identify the human during cooperation with the machine? And the answer is yes. So we can do this. And this behavior can then be described, generalizes a little bit better, and then these traditional approaches. So this has been said just to explain that as for a simple system, suppose A and B is given. Now, I just want to compare how good the method is. Given a system which is or given the ground truth. Ground truth means we as researchers know the truth, but our algorithm does not know Q and R. So our aim is to identify exactly Q and R built on measurements, right? And then we can compare whether we are good or not. So if we do the calculations, we solve the forward problem, and then we try to identify the backward problem and look what happens. Now, it's interesting. Here's the result with the IOC method, just roughly described before. You get this and that. So perhaps it's obviously not the same, right? But it's similar. Perhaps you see something, whether it's similar. Scale, exactly, scale. It's the same result. So it's an objective function, which is produced here, which is almost the same, which is given here, but scaled with factor 2. And therefore, it produces the same trajectories. Interesting, during our research, we were able to define all possibilities of objective functions which do the very same. So at the very end, we can have all these objective functions in our hands. Well, this is an example, and I want to explain one particular example, human movement explanation for human-machine collaboration, where we do our research. This is something I already talked about, this behavior cloning approach with the problems of generalizability or optimality principles. These are the two ways of doing it. And well, if we say it's an optimality principle, it can work as follows. And there are basically two views in neuroscience over the last years or decades, I would say. A so-called way how automatic autonomous driving is constructed. It's a so-called open loop approach. Suppose a human has to go from this point to that point, from the origin to that. So I do a hand-arm movement, for example, for grasping my cup of coffee, right? So from here to there, I want to grasp, I have this movement. Now we have the problem, just to explain why it's a problem, the human can do it this way, that way, or that way. And the question is, why am I choosing exactly this? And the answer is, yes, I do it in an optimal way. That's the answer of neuroscience, and it's undebated today. Well, and then the question appears, how is the human doing that? And the latest, or almost latest approach was, or before completely different on the right-hand side, it was the following. Well, the human first looks at the scenery, A and B. I want to go from A to B, or here's A, there's B. He produces a trajectory in his brain, and then it's trajectory tracking, like a tracking control. Right? So there's somewhere in the brain, there's a trajectory generator who says, if you want to go from A to B, there's some sort of optimal control problem, which follows exactly this curve. And then there's a control strategy, which brings my hand, all the joints, and activates the muscles that I stay on this trajectory. Okay. And unfortunately, this is not true. Sounds easy. First of all, nobody was able to discover a trajectory generator in the brain. Second, you can also observe things. I come to the second later. Here you have a true experiment with one person trying to hit a point here, starting from there. The trajectories look like that. And so if I ask you, and I measure that, we have the facilities in our lab, we can put markers on you, and we can measure your performance. Well, and I ask, well, we'll grab this pointer here. Then I will do it, and I do the experiment 20 times. I grab the pointer, I grab the pointer, I grab the pointer. And then the following happens. Well, I grab the pointer every time. So only in the case I'm drunk, then I'm not able to do that. But usually I hit the pointer very precisely. So if you ask to hit a point exactly, you're able to do that. It's like playing tennis. Who's playing tennis? Somebody? Well, you hit the ball, right? If normally. But if you measure the trajectories, they're completely different in between. And this is a second type of describing the behavior. It's a so-called closed loop approach. You have the biomechanics, and there's just the endpoint given to the human brain, and the human does not rate what's in between. It just accounts for the endpoint accuracy. And the interesting, that's somebody we have projects with Sports Institute in Freiburg together. And I asked, why is that? And he said, well, it's more counterintuitive. If you try to be if you learn something new, so I'm new in tennis. Yeah? So then I activate everything, all my muscles. I'm on the trajectory, try to hit it. If you have a super tennis player like you, perhaps, well, the variance in between is huge, the better you are. It becomes higher, the better you are, but you become more precise, the better you are. So it's endpoint accuracy. And if you do the story on the left-hand side, just the human always follows the trajectory, it will not describe that. There's a physical reason for that, because the human, I learned that from the sports guys, the human tries to be as energy efficient as possible, and usually you have two muscles to control your movement, and there's only one muscle activated. Therefore, you get one of the muscles relevant for that, and due to the fact you have this kind of variance, and only at that point you activate it. Therefore, sports means training and to reduce muscle activation. So that's only the right muscles, better to say. So there's a justification for that. And in Nature, in 2004, there was the first guess on that by Scott and later by Todorov, and 2009 also a Nature paper, where one realized it's a good idea to do that way. So unfortunately, to what I said before with the inverse optimal control approach, while we were able to identify more or less the trajectory generating principle, unfortunately not the variance, right? So it's obvious that it's necessary to not just, we are not able to describe the movement correctly. So I just want to explain that. Suppose you have this performance index, and you do something, have a system like that, and well, we go about this, and you do this typical bi-level approach I mentioned before. The red one is GT, stands for ground truth. Obviously, there's a deviation, right? Right inside inverse optimal control, ground truth, and another inverse optimal control procedure. Well, there's still a deviation, even if you did the best you can do. So the movement of the human is the red one, and even if you do IOC methods, whatever you take, bi-levels, you will not hit the situation. Why is that? Because the human behaves, unfortunately, according to a stochastic optimal control problem, where the stochasticity becomes relevant, and the closer you are to the final object, the less variance you have, and in between you have huge variance. So it scales over your movements. And that's something you observe. The faster you are, the less precise you are, for example. So the problem appears, is it possible to identify not only a Q and R, but also the covariance matrices of the stochastic process, because they are relevant for the movement of the human. So if you want to do it right, you should, it's a good picture. You should account for this variability in between. So our attempts with IOC were good, but not sufficiently well for doing it properly in other aspects. That was our observation. And the interesting fact, if we do that, I just want to give an example. Again, you only look at the picture and not the procedure. Here you see the ground truth with a stochastic inverse optimal control thing, which has been elaborated during the last 2 years. And there you hit the trajectory. If you do, I don't have a IOC result. It's completely different to that. You get that. And well, of course, if you have stochasticity and you do something like the bi-level approach for such a simple problem, just 2x2 system, it takes you 900 hours to do the bi-level approach, and we were able to boil it down to 20 hours. That's the state of the art right now. Well, this is my advertisement slide. So if you're interested in something like that, if you're interested in human-machine cooperation, this is necessary. Why it's necessary to have these kind of white box models? I just want to give some sort of motivation. We work with a huge company together, which is doing medical devices. The KIT is working with such a company, which is somewhere in the North Campus, located with a innovation hub. And well, it's if you want to do medical devices where the human is perhaps assisted with robots in a similar way, so there are two operating somewhere in the human. You can imagine that strategies which rely on neural networks are not so in favor of them, because you have to have this legal requirements. You have to verify that it doesn't happen something unsafe. So they're very interested in doing these things. And so it's interesting to know what the surgeon is doing when using his scalpel and cutting somewhere. And so it's important to have white box knowledge from a legal aspect, from our perspective, also from a performance aspect, because under this condition, it's perhaps easier to get it approved by authorities so that it becomes a real product. So if you're interested in that, in such things where you have this kind of human-machine cooperation, learning something about the human in the forward, also in the backward problem. So inverse, you try to identify the human. If you want to do human-machine cooperation, then please feel free to contact me personally or the group leader, Balint Varga, because in this group, we have these type of things. It might be also done in a human-centered design when you use tools. For example, here you have a tool. There the person were asked to drill holes in a specific angle, and there's a robot assisting him. That was the experiment. And obviously, it's difficult to do. There are two persons or two agents working, the human and the machine all together. Obviously, it's necessary to understand the human's movement and in question, etc., etc. So if you're interested in that, please feel free. And one project I've not mentioned here, you have a situation where a patient is guided from one operation theater or some practical help from one room to another by means of a robot. And this is harmful because instead you must have used somebody else. Okay, so if you're interested in that, please feel free to contact us, but also Philip Karg and others in the group. So have a look at that. So that's the point for that. Just here, I wanted to stop. Now, go on with let's explain. It has been working. Okay, some words about our examination at the very end, and then a last advertisement. Please stay. It's hopefully also interesting. Some words about the examination. It's about understanding. It's not about calculating, right? It's important. So if you calculate, it's always to understand whether you understood, right? Please do the examples more from this perspective. It's in particular ask the tutors, so basically Mr. Giesler, with regard to that. Try to capture the basic ideas. Try to capture, of course, some knowledge is necessary. So obviously there are some facts which have to be trained. I think they are well listed in the Fachschafts lists on slides. There's short story. Somebody lost his this list of the Fachschaft a couple of years ago, and in my office, and I thought it was a good idea to look in it because there's also something described about me, and I found it really funny because I read it, of course, yes, I wanted to know what's standing in the list there, and he always looks angry, but it is not that problematic. So, That's true. So if I'm looking a little bit frustrated, it does not, well, it doesn't, it's not necessarily you, that's introducing this frustration. Sometimes it's due to the fact that I'm thinking about something different, or because I always have to think a little bit ahead of your answers because my next question has to appear somewhere. I'm concentrated. Just it's well, but if when I'm asking, well, there might be something mysterious about your solution, then please feel free to rethink your solution. It's usually I'm not trying to mislead you somewhere. It's not nothing. Hey, you said A, perhaps it's B. What do you think about B? This might happen more on the element of discussion, right? So that's perhaps the most important part. Of course, there are some calculations, but tiny calculations, of course, due to the fact that we have just 20 minutes. 20 minutes. If it's your first oral exam, might also be the case. Please tell me that, because usually it's the first situation. You're sitting there and there are two. You have to answer to in front of two. It's perhaps a little bit, you're a little bit nervous. So tell me that. It's also helpful. Okay. Well, that's it. Do you have questions at that point? Okay. So now my last advertisement, due to which I had so many problems at the beginning. Hopefully it's working right now. I try to. Let's see. Well, this is, yes, of course. Of course. Sorry, the language, you choose the language. Almost. German, English, French, it's okay. Unfortunately, I don't speak Chinese, Japanese, or yeah. That's okay. Let's hopefully start with that. Let's see. Perhaps it's working somewhere. I try it again. 5 minutes about this. Mensa is full right now. 5 minutes. I just want to explain the idea. What is behind that? When I started here at KIT, I asked students like you, what will you do after your master? And they said, I go to Bosch. If I work a lot with MIT and Berkeley, and so if I ask the students there during my BMW time, but also now, and if I ask the students, they told me, well, I found a startup, and I thought it's quite. Where's the problem? Because we have so many facilities here at KIT which facilitate entrepreneurial spirit, and the problem is, I think that it does not fit in your syllabus, so in your courses, in your course plan, and all that. And this was a starting point to convince the federal ministry of the German government to say, well, we should produce something which perfectly fits into the core syllabus of students, and to reduce the fear of being an entrepreneur. This is one perspective, and this is a lecture, a module, of which you can elect for your studies. I will explain two more things on that, but there's and the idea is to create something. You don't need to have an idea. You can come only open-minded. You will be trained to generate your own idea there. Well, I want to compare this a little bit to what you have learned during your student life. Usually, you know, labs. There are experiments well defined afterwards. You do the lab experiment, and then you do the protocol, and then you're tested, and the professor verifies. You know, perhaps other lectures where the problem setting is a little bit more free in that sense that this is the problem, but you can choose the methods. Well, in the traditional labs, the methods are given, the problem is given, everything is given, and you have to follow like the recipe and to process. Yes, I did this, and well. And here, everything is free. You choose what you want to do. You choose what methods you like to use. And at the very end, it can be elected in your studies. So you can put it in. So it's the maximum freedom, more or less. What we are doing is we try to guide you, and therefore it's in a master at that point that you're able to apply everything you learned, if you like, and do something you really have fun with. The problem with that, if you have fun, you spend a lot of time. But one of the most impressive results during the questionnaire of one group, somebody said it's like working in the Silicon Valley, but at the KIT here in Karlsruhe. And this was very, very helpful for me because it worked. And I want to tell you one story because we have usually, by the way, it's not the intention that you found your company at the very end. It's just to train. It should feel like you found the company at the very end. On the other hand, we have every year at least one group of students who does or who founds a company and wins prizes, etc. And one example I want to tell you, because I think it's very, very intuitive and helpful, was one of the groups really, really inspiring out there. And you know, there are blind peoples, right, around there, and they have this stick to look whether there's something. Well, I tell you how this works with the stick. It's like that, okay? So you're going around, and trying to, okay, there's something, I don't go there. Now, what happens if you have trees or something which are here, fresh? And I thought, well, this will never happen because there are no trees on the streets and something. And well, this group figured out that no, 30 to 40% of injuries of blind people are due to that fact because they smash into buildings, into doors, into something which is not present, in particular trees, plants, other objects. Well, you can look for that if you look at them. So we need something, and they constructed a lens which indicates whether there is something. They have small cameras in it, and then vibrates on the left-hand side or right-hand side of the head, and so you can navigate through these difficulties. What is special about that? It's not just the idea. At the very end, you have to present your prototype. So you build it really. You make it real. So there was a lens, 3D printed with all the electronics, cameras, and the algorithm present after 1 year. So if you have interest in that, I just want to show you that. There is, on the one hand, you can apply for that, but there's also, I hope it's on the next slide. See it here? No. But on our, please visit our website. So therefore, it's perhaps a good idea to know that because at the very end of this lecture, there's a pitch. 5 minutes, like elevator. You're staying in the elevator at 5 minutes. It's long. It's not this elevator. Oh, it's this elevator because it's so old. During these 5 minutes, you have time to present your idea. And this pitch session with industry companies, former startups, venture capitalists takes place this Monday, coming Monday. So if you're interested, please feel free. There's a YouTube channel. You can watch that and look. So you get an impression what's going on there. And if you're interested in that, please feel free to contact this website. There's everything online. And that's my last word. And now you have time to go to something to eat. By the way, this was the last lecture. So next week, no lecture at all. We finished our lectures. Thank you.